Let me start with a couple of announcements. Next week, we do not have a formal talk or a lecture. We have the second in what we call the Energy Open Houses, which is a networking event where faculty, staff, and students come in basically to eat pizza, but then also talk a little bit about energy teaching and research on campus and network with each other, learn from each other. So that's next week. 2 weeks from now, we have Ryan Weiser from Lawrence Berkeley Lab coming to talk to this symposium, and the title of his talk will be United States Renewable Energy Electricity Futures, Are High Penetrations Possible? And he'll present a combined technology, engineering, and policy perspective on how much and how fast can renewables penetrate into the existing infrastructure in the US and what changes need to be made to this infrastructure to accommodate more renewables. It should be a very fascinating talk. It's a tremendous pleasure to introduce our speaker today, Professor Richard Lester. Professor Lester is the Japan Steel Industry Professor and Head of Department of Nuclear Science and Engineering at MIT, where he has been a faculty since 1979. He is also the faculty co-chair and the founding director of the MIT Industrial Performance Center. His research focuses on innovation management and policy with an emphasis on the energy and manufacturing sectors. He is currently leading the Energy Innovation Project at MIT, which is a very large effort for studying a strategy for upgrading the US energy innovation system. I was going through his CV, and he has a very, believe me, he has a very long list of distinguished accomplishments. It will take me several minutes to actually go through, but I'll just note a few things here. He has written or co-written a number of widely cited reports, including The Future of Nuclear, which came out in 2003, and The Future of Coal. If any of you who have worked in energy or have read papers on energy, more likely than not, you will find a reference to either of these two studies. He has also written or co-written at least 7 books. That's what I could find from your website, Professor. 7 books, and I'll name all of them, actually. Innovation, The Missing Dimension. Making Technology Work. Global Taiwan. The Productive Edge. Made by Hong Kong. Made in America. And the last one, Made in America, is actually the best-selling title in the history of the MIT Press. So you can imagine the impact these books and his work has had in these broad and very important fields. The latest in the chain of Professor Lester's path-breaking books is Unlocking Energy Innovation, How America Can Build a Low-Cost, Low-Carbon Energy System, which came out in 2011, a couple of years ago, from the MIT Press. And that's what Professor Lester is going to talk to us about. He has an undergraduate degree in chemical engineering from Imperial College London and a PhD in nuclear engineering from MIT. Please join me in welcoming Professor Lester.
Well, thank you, Professor Ryan, and really many thanks for the invitation to come here. There are a lot of reasons to want to be in Texas and in Austin. I actually have never been to Austin before, but one of the reasons is that a lot of interesting things seem to be happening here in the topic of today's session, energy innovation. And I hope that in the discussion we'll have a chance, I'll have a chance to learn some more about what's happening here, because I suspect that some of you are pretty much involved in that. It's a big and complicated subject, so I'm actually going to begin at the end with 4 points that I'd like to think that you would take away from this session. I mean, there'll be other points I hope you'll also take away, but there are really 4 points that I want to emphasize. The first is that the scale of the innovation challenge that we face over the next few decades is much bigger than many people recognize, even many experts in the field recognize. And our innovation system isn't remotely up to the challenge today. And I want to talk a little bit about what we might need to do in order to change that. But the second point I want to make is that at least in my view, this challenge, this very large challenge, actually is within our grasp. If we're as willing to be creative about the design of the institutions for innovation, the system of innovation, as we obviously must be about the technical innovations themselves. And I'm going to focus, if we have time, on two aspects of that redesign of the institutions. The first is structural reform of the electric utility sector, which, whether we like it or not, is going to be on the front lines of the innovation challenge. And here I'm going to make an argument, if we have time, to shrink the footprint of the regulated electric utility and to shift towards a system in which the utilities increasingly become what some people have called smart integrators of low carbon supply and demand resources. But the second point about institutional change is that we know that markets left to their own devices won't bring about the acceleration of innovation that we need and that I'm going to talk about, but that the federally driven system of promoting energy innovation that we've relied on over the last several decades won't work. And I'm going to argue that we need to shift to a more regionally based architecture. Now, again, this is not a talk about particular technologies. I'm an engineer. I think some of you here are also engineers, and engineers like to talk about particular technologies. But I'm not going to do that. We can come back to that, if you like, in the Q&A. What I really want to talk about here is the system for innovation. And by that I mean the whole complex of indirect incentives, direct government support, regulations, educational institutions, research institutions, codes, standards, markets within which new technologies are developed and taken up by energy suppliers and energy users. That's the focus of what I want to talk about. Now, to set the table, I want to stipulate a few things. One is that I think it's useful to remember, as we sit here in Austin and in Texas, that the most important natural resource in solving the world's energy problem isn't oil or gas or wind or whatever. It's brain power. It's human ingenuity applied to finding better ways to extract, convert, transport, and use energy. Of course, we don't just have one energy problem. We have at least 4 separate problems, each one on its own, very difficult to solve. And when we combine them, since the solutions to one problem will sometimes make the other problems worse, the overall challenge is not, it's more than additive. This is a situation in which the whole is greater than the sum of the parts. The first problem is the rapidly growing need for affordable, reliable energy supplies around the world. Most projections suggest that global energy use will have likely increased by at least 50% by mid-century, and electricity use will have more than doubled, which of course is going to create great pressure on energy prices and supplies. Now, that is not a scenario of irresponsible consumption. We all recognize that we're living through a period of really quite extraordinary economic growth, unprecedented indeed in human history, in which hundreds of millions of people are lifting themselves out of poverty and starting down the road to a middle-class standard of living, all within the span of a few decades. And one of the consequences of that, of course, is sharply increased energy use. But in case anybody thinks that, say, a doubling of electricity use by mid-century implies profligate consumption, let me point out what this would mean. Roughly speaking, it would mean that the richest billion of the world's population at that time, which will be about 9 billion, will be using electricity at about the same rate that the average American uses electricity today. The middle 7 billion would be using electricity at about the same rate that the average Chinese uses it today, which is about a quarter of our use per capita. And the poorest billion would still have no electricity at all. That's what a doubling of electricity use by mid-century will mean. And to me, that doesn't seem profligate. So that's the first problem. The second problem is that the world's increasing dependence on oil and gas to meet this demand is going to mean increased economic vulnerability as well as greater international tensions and the potential for conflict. There are likely to be significant shifts, geopolitical shifts over this period, and it is interesting to speculate on what the possible emergence of U.S. energy self-sufficiency might mean for security arrangements in the Persian Gulf and other parts of the world. But the problem of energy security is surely going to persist globally and indeed is likely to intensify. The third problem is that coal burning for electricity and industry and oil use in vehicles are the main culprits when it comes to severe urban and regional air pollution, SOx, NOx, hydrocarbons, particulates, and so on. And some of you may have seen the recent report on health effects published in The Lancet, the British medical journal, that reported that in the year 2010, outdoor air pollution, much of it associated with energy use, contributed to 1.2 million premature deaths in that year in China alone, and 3.2 million deaths worldwide from that. So that's a third big problem. And the fourth problem is that of climate change. How can we meet the rapidly growing need for affordable and reliable energy without wrecking the global climate? I take the view that this problem, the problem of climate change and the transition to a low-carbon energy system, is the most important and most urgent problem that we face in the energy sector, as well as being the most difficult one. But I also acknowledge, and we need to recognize, that for much of the next 40 or 50 years, which is the key period for dealing with this issue, climate certainly isn't going to be the only issue on the energy agenda. And indeed, for much of the time, it's not likely to be the one that has the highest priority either. And so we can't assume, a sustained, laser-like public policy focus on climate change over this period. And I'm going to come back to what that might mean for the design of policy. In fact, some people, very sophisticated people, aware of the tremendous scale and difficulty of this transition to a low-carbon economy, have been refocusing their attention away from the problem of mitigating carbon emissions towards the problem of adaptation. The best of this adaptation work is very sensible. If the costs of adapting to climate change are less than the cost of preventing it, then it's certainly a good reason to focus on adaptation. It's also worthwhile to ask which adaptation approaches are most efficient and effective. If, for example, you live in Bangladesh, does it make more sense to increase the height of dikes or to invest in hospitals to treat the very young and very old sufferers from heat stroke and exhaustion? Those are serious questions, and it's important to think about them. In practice, the most effective strategy clearly will involve both mitigation and adaptation. John Holdren put it nicely recently when he said, we need enough mitigation to avoid the unmanageable and enough adaptation to manage the unavoidable. The problem with mitigation, of course, is that today most low-carbon energy supply technologies are still too expensive, too difficult to scale, or have other drawbacks. Here's a picture. These are, I don't think you can see very clearly, but this is the levelized cost of electricity from alternative supplies or technologies. The three at the end are fossil. Everything to the right is low carbon. That's the problem. In principle, there are three possible responses to this problem. You can mandate or subsidize the adoption of the low-carbon technologies, or you can make the high-carbon incumbent technologies more expensive through some sort of tax scheme, cap and trade, carbon tax, whatever. Or thirdly, you can innovate so as to reduce the costs of the low-carbon technology so that they become more cost competitive. And so to oversimplify, but not really by very much, you can either increase the price of the bad things, which in this case are high-carbon fuels, or you can reduce the cost of the good things. For many years, the debate here in the US has been dominated by that first idea, increasing the price of the bad things. And Bill Nordhaus, so you may have read some of his work in this class, the economist from Yale, put it recently. To a first approximation, he said, raising the price of carbon is necessary and a sufficient step for tackling global warming. The rest is largely fluff. Now, that's good economics, but of course there's a problem with it. Politically, it hasn't worked, at least not yet. And there are several reasons why it hasn't worked. One of them is that the price that would be needed to induce the innovation at the necessary rate would be too high for any politician with an interest in being re-elected to really support, or most of them. In the end, a carbon price of some kind is going to be essential. But we also need more direct approaches to accelerating innovation. And if that's what Professor Nordhaus means by fluff, we're going to need more of it. And so that's really what I want to talk about. But let me first digress a little bit and say, or ask the question, how big is the task? How big is this innovation problem? 4 years ago, when President Obama was first elected, he, as some of you may remember, he and the other leaders of the G8 countries, it seems like a long time ago, but they agreed that they should reduce their emissions, the rich countries should reduce their emissions of carbon by 80% by mid-century. Now, we all know that he soon stopped talking about this, and for the next 3 or 4 years, the question of climate change was put on the back burner, although it would be wrong to say that nothing happened during that period. One very important development was the administration's new auto emission standards that will almost double fleet average miles per gallon by 2025. So it's not that nothing happened, but it certainly was pushed off the front burner. Since last fall's election, climate change seems to be moving back up the list of the president's priorities. So it's worth asking, why did the president and those other G8 leaders talk about an 80% reduction back in 2009? Why 80%? And what would it take to get there? So here's an answer to the first question. Climate modelers estimate that if the atmospheric concentration of carbon dioxide were to be stabilized at about twice what it was before industrialization began, around 550 parts per million, there's a roughly 50% probability that the global surface average temperature increase will be no greater than 3 degrees C. There's a 50% probability that it will be greater than 3 degrees C, but that's the midpoint of the estimate. Many people think that this wouldn't be enough. A temperature increase of 3 degrees C would be more than 3 times greater than what we have already experienced over the last few decades, which is very likely the result of previous greenhouse gas emissions. And we have already, of course, begun to incur significant damage as a result of this. Moreover, as we all recognize, I hope, the climate models are very far from exact. There are still many uncertainties, and while the mean expectation for a 550 parts per million atmospheric burden is 3 degrees C, the tails of the probability distribution are very long. And this means that we might be lucky and that things will turn out to be better than expected. But of course it also means that there's a chance that the actual temperature rise will be a good deal higher. Some people have set a more stringent target of 2 degrees C, but that's actually already probably out of reach. So for now, let's just take that 550 parts per million goal and the 3 degrees C that goes with it. If we want to stabilize at that level, it probably means that global emissions in the year 2050 will have to be at least 25% lower than they are today. You could get to 550 in a number of ways, and there's nothing unique about this. But roughly speaking, we could say that we would need to be reducing global emissions by about 25% by mid-century. Now, since the world's population by then is expected to rise to 9 billion from today's 7 billion number, what this means is that the average per capita emissions would need to go down from where they currently are, which is about 1.3 tons of carbon per capita worldwide. That would need to go down to about 0.77 tons of carbon emitted per capita worldwide. If we were to further say that all nations, rich and poor and medium income, should achieve that global average number for per capita emissions. Now, many people would view that as being only a minimal interpretation of what global equity would mean, having everybody do the same. Other people wouldn't view it as equitable at all. But let's just say that we thought about a world in which all nations, rich and poor, would be emitting at the same rate. That would mean that the US, which currently emits at a rate of about 5.5 tons of carbon per capita per year, would have to reduce its overall emissions, not now per capita emissions, overall emissions by about 80% by mid-century. And by the way, we can do exactly the same calculation for China. And of course, on a per capita basis, China emits much less than the US, but now is the world's largest carbon emitter, and which together with the US accounts for about 43% of world carbon emissions. If it were also to lock into this, and that's actually, I should say 0.77, not 0.63, that's a typo. But for China to get down to 0.77 tons per capita, it would have to reduce its global or aggregate emissions by about 60%. So how difficult would that be? Well, we can gain a little bit of insight into this by just thinking about US coal use. We produce and use about 1 billion tons of coal in the US a year, and it accounts for about a third of global carbon, US carbon emissions. Most of it is burned in coal-fired power plants, and today those plants are generating a little under 40% of US electric power. As you all know, coal is delivered to these power plants mainly by rail, And those rail shipments account for about a half of everything that gets moved on U.S. railroads each year. If you take all the coal that is delivered each year to U.S. power plants and put it in a single train, how long do you think the train would be? Somebody? 500 miles. 95,000 miles. About 4 times around the Earth's circumference. If that was, and in order to, in order to reduce our carbon emissions significantly, we're going to have to get rid of most of that coal. So that's a kind of a, now suppose we were to do what we've been doing a lot of recently over the last few years, backing coal out of our electric power system with natural gas, low cost, much cleaner, and significantly less carbon emissions than coal. If we were to continue what we've been doing, which has brought coal, the coal contribution to U.S. electric power down from about 50% just 3 or 4 years ago, down to below 40% today, if we were to continue and get rid of all the coal and use natural gas instead, we would still only reduce our carbon emissions by about 20%. And the President's talking about 80%. So this gives you, I think, some sense of the scale of the problem. Now, we can actually gain a different kind of insight from this very simple identity. This isn't even an equation. It's an identity that was first pointed out 20 years ago by the Japanese electrical engineer Yoichi Kaya. And maybe you've talked about it in I don't know whether you've talked about it in class. It's a very useful way of thinking about things. And he pointed out, Kaya, what it says is that the carbon emitted by any jurisdiction, that's C, whether it's a city, a state, a region, a country, the world, you name the jurisdiction, you can express that in terms of 3 quantities. The carbon intensity of the economy in that jurisdiction, that's how much carbon is emitted per unit of economic output. The productivity of the economy, the economic output per unit of labor or per person, and the population. So using this very simple identity, what it says is that if the U.S. were to achieve what the President 4 years ago said we ought to try to achieve, 80% reduction in carbon emissions by 2050, and if we also want to have an economic growth rate of 2% per capita per year, now you might say, well, is that good? Is it bad? It's about what we've been doing over the last few decades. It's actually better than what we've done over the last 10 years, but nobody really thinks that's an acceptable economic performance. So let's say 2% per year between now and mid-century. It's fairly modest, but it's about what we've been doing on average since the 70s. And also, since the U.S. population is expected to grow at a little bit under 1% per year between now and mid-century, what this means is that we would have to reduce our carbon intensity each year by about 7%. And compare that with what we have been doing over the last couple of decades, that's about 2% per year reduction in carbon intensity. So in a sense, this gap between 2% and 7% is the magnitude of the energy innovation task that we face. That's sort of what we have to do. And it's going to require both a rapid acceleration in the rate at which the energy supply system is being decarbonized and a rapid decline in the amount of energy used per unit of economic output. Now again, we can go through exactly the same exercise for China. There, of course, the aspirations for economic growth are much greater. You know, the Chinese government or agencies within the Chinese government are talking about 6% per capita per year growth rates, and it's giving some of the Chinese leadership heartburn because they think that's too low. They're worried about being able to maintain political control with an economic growth rate of 6%. But if we take 6% and if in addition China was to set this goal of achieving this global average per capita number of 0.77 tons of carbon per capita by mid-century, and given that China's population is expected to remain roughly stable or maybe even shrink a little bit between now and mid-century, China would need to reduce its carbon intensity by about 7.1% per year between now and 2050. It's about the same as what we would have to do in order to achieve the same goal, despite, of course, the huge difference in our respective economies, differences. It's worth noting that the former Prime Minister, Wen Jiabao, announced recently that China was going to try to achieve a 5.8% reduction in its carbon intensity over the next decade. That falls somewhat short of what we calculate they would need to do, but it's actually quite impressive. And indeed, if you compare it with what we sort of say that we're going to do, you know, it's no less compelling, no less convincing than what we talk about here. Of course, it isn't going to. We all recognize that it isn't going to be enough for China and the U.S. to reduce their carbon emissions alone. Everybody else is going to have to do it too. But unless these two countries together take decisive action, it doesn't matter what anybody else does. We're going to face very severe damage. So the question is how to close this gap. I think, or a useful way to think about this problem is in terms of three successive waves of innovation. The first wave is mainly about improvements in energy efficiency. We can probably do those fastest. They don't rely to the same extent as the other waves on breakthrough technology. It's really more about new business models, new institutions. The second wave will overlap with the first, but the first must, of course, continue. But especially after the year 2020 or thereabouts, we're going to have to start to see deployment of the main low-carbon supply technologies, nuclear, solar, wind, carbon capture and storage, on a much larger scale than anything we've previously seen. And then the third wave is about something that we might hope to see, which is developments that draw on fundamentally new advances in things like materials and catalysis and energy transport. In the best case, these things would overturn long-standing physical limits on energy storage and conversion. I'm talking about things like artificial photosynthesis, maybe air capture of carbon dioxide, maybe even nuclear fusion. But let's not forget that the long lead times required to translate breakthrough research into commercially viable technologies and then to achieve significant market penetration after that, what all that means is that these breakthroughs aren't likely to be making major contributions much before 2050. How do we get these waves going? How do we get them going? Now, if you listen to the debate, you hear a lot of different perspectives. The techies say we need more R&D money. The visionaries say we need a Manhattan Project or an Apollo project. Economists say we just need to get the price right and things will then, the market will work. The wonks say we've got government that doesn't work, let's reform the government. And the culture warriors say the only way this is going to work is if we change people's behavior. What's missing, these ideas aren't actually wrong. None of them is wrong. But what they lack is any sense of how innovation actually works. And here, we do need to go beyond the popular narrative, the stereotype that the lone entrepreneur in his basement or garage, because nobody does this on their own. And I mentioned at the beginning this supporting system of institutions for various things. And for the US as a whole, this set of innovation-related institutions for intellectual property, codes, standards, markets for capital, all of that has worked pretty well on the whole across the US economy. But in the energy sector, it has worked less well. And the biggest problem that hasn't yet been solved is the problem of public action. We need public action because the energy marketplace, left to itself, will fall short of what's needed in this area because we're not pricing these needs into the transactions between suppliers and users of energy. On the other hand, the federal government is hamstrung. It isn't just that we have a dysfunctional political environment in Washington, and it isn't only that the poor state of the nation's finances doesn't seem to lend itself to major new federal spending initiatives. Both of those things are true, they're both facts. But even if they weren't facts, there is also the fact that the government's track record in promoting energy innovation over a period of decades has been mixed. There have been successes, but there have also been failures. And it's a track record that, if you really look carefully at it, doesn't inspire confidence that the problem of public action would be solved even if we could finance or fund federal programs on the necessary scale. So I just want to break the problem down into 4 parts, and then maybe we can have some discussion. It's helpful to sort of figure out what needs to be done to recognize that these innovation can be thought of as having 4 components. This is not the usual, by the way, linear view of how it works. But it is useful to say that we have the creation of new options, the discovery and development of new technological possibilities, the determination of whether these possibilities are viable in the marketplace, think of that as demonstration, then cost reductions and other improvements that happen in the early stages of commercialization, the initial stages of adopting the innovation in the marketplace, and then finally continued refinement of the innovation after it has begun to be used on a large scale in the marketplace. I don't really have time to explain why this isn't the same thing that anyone who has studied innovation has seen traditionally, but this isn't really the traditional linear innovation model. I just want to make the point, though, that if we want to accelerate innovation, it isn't going to be enough just to focus on one of these things. So people say, and they're right, we need to spend more on research and development, particularly fundamental research. Many groups have concluded that we're spending probably a factor of 3 less than we should be on fundamental research and even applied research in the energy area. But even if we did that, let's say we increased our R&D spending by a factor of 3, much of the force that more spending might exert at the front end of that process would simply be dissipated unless we also address these downstream stages of the process. And it's really at the intermediate stages that the problem is hardest to figure out. At the front end, most people would recognize that we have to rely, on the one hand, on federal spending, on fundamental research, and risk capital, venture capital, for the early stages of new option creation. At the other end, the improvements in use end, we also recognize that that's really got to be about companies in the marketplace spending their capital to improve performance. But the intermediate stages, we don't have any sustainable solutions to that problem. We don't even really have a good way of talking about those intermediate stages. Now, we had, of course, during the stimulus period, a 2 or 3 year boost from the federal government spending, but that's essentially over. And now we really don't have a clear picture about how to accelerate these intermediate stages. I want to ask Varun whether at this point I should stop talking and throw it open to discussion. And so let's have some discussion. The one thing that I didn't mention that I was planning on mentioning was I actually have a solution to this intermediate problem. It's not really a solution, but it's a set of ideas about how one might attack it. But maybe towards the end of the 15 minutes I'll mention it. But for the moment, let's just have... Well, I don't want to take time. I think let's have 3 or 4 questions on the table, then I'll come back. I will come back to it. Yes, sir.
So with this slide that you're showing here,
yeah.
What popped into my head was I think there might be a lot of people who wouldn't put enough trust into this because it's one thing to kind of start, somewhere along the line, but then I think a lot of people naturally would like to kind of judge how things are going, so they might not want to put that much faith into the following 3 steps.
Faith into, what do you mean faith?
Faith that it will work, because I guess it's kind of like investing in this long project. So and you're saying that the effort will be somewhat wasted unless you actually have all 4 points.
Yes, but I agree with you that, and it's a very important point that I think you're making, that the risks in these intermediate stages are very high. And so we've got a problem, we've got a requirement for high levels of investment, because if you do demonstration of, I don't know what it is, let's say a new nuclear technology or carbon capture, even to build a single demonstration plant, $1 billion, or at least a few $100 million.
Right.
High risk. But I think your point is that the risk is likely to deter people, but I hope your point is not that we don't need to do those things.
Oh, no. It was just a question. I meant, kind of how do you think that we could overcome the fact that it might deter at least some people?
So we have to find a mechanism that meets a number of, well, here are some of the things that our mechanism would have to, these are some of the criteria that if we can imagine a mechanism that solves this problem that you're talking about, we would want a number of things to be the case. We would want the scale of whatever the financing mechanism is to be comparable to the scale of what we need, right? And that's both scale of individual facilities, which could be as much as $1 billion, and then you've got a few that you have to build in the early adoption stage. But there's also the aggregate scale of this, enormous energy transformation that we have to accomplish. We'd want space for new entrants. We know that when innovation works, when we get a lot of innovation in our economy, there are opportunities for new players to come into the system. It isn't always the same old people. Often the same old firms are the ones that don't innovate. We need competition. We need something that we don't always get from federal programs, which is stopping things when they're clearly not working. And there are a lot of the failures that we've had in the area of energy demonstration projects by the federal government is that they've kept on going long after it's been clear that they weren't the right direction to go in. We have a number of other things that we need, but the key thing that I guess I'd like to suggest, and then we can maybe have other questions, is we can't rely on the federal government to do this. Not only does it not have the financing that would be required to do these intermediate stages, but when it has tried to do this in the past, it hasn't done it very well.
So you're saying that's kind of what's different about that, about, you know, why that's what sets this apart from other failures or potential failures.
I mean, I guess what I'm saying is that we've been trying to do this for decades by relying on federal demonstration programs. And you can look at the history of nuclear and the history of solar and the history of carbon capture, and it hasn't worked very well, and we need to find some alternative mechanisms to deal with this. We can't walk away. We can't say, just invest in front-end R&D, and if we just increase our R&D spending by a factor of 3, that will solve the problem. It won't, because we've got to be pushing forward through all of these phases. So that's really the...
Okay.
Yeah.
Hi. I think my question is still about this stages. So for solar photovoltaics, I guess right now we are on the stage of early adoption.
Yes.
And at this stage, I guess both the federal government and the state, majorly the state government has invested a lot of money in the form of all kinds of subsidies. But still, I think it's not enough. So what are the new ideas in your new scheme that can help us to meet the gap you mentioned at the very beginning? Since I guess we're still kind of using the same form, but it's still not enough. Mm-hmm. Thank you.
So let me take a couple more questions and I'll come back and address this. Yeah.
I guess mine is more of a comment than a question, and it's directed to your third bullet in your next slide, which is has to do with a new entrance, and then your previous slide, which maybe it would be good if you could go back to it. The people have different categories of people who think they have the solution. Yeah, the techies, visionaries, and so forth. From my perspective, there's another one to add to the list, which is perhaps the scientists and the sociology of the way we do science. And it isn't just about more money or even a Manhattan or an Apollo project, but it's the way that we deal with totally new innovation with the sociology of science and the whole peer review process. I think that the entire way that we do science that leads to these things may also, in fact, be broken because of the very high penalty that people pay when they enter into fields that are out of mainstream science and that are rejected by mainstream science, and the total inertia that goes along with that process of how we do science and how scientists interact with the peer review process and so forth. It appears to me may very well be broken, because if you look at the history of science, most of the real breakthroughs that have been for the human public welfare benefit have been radical in nature, and almost all of them have been initially rejected by science, and there's not room for new entrants. For example, it wasn't until the Wright brothers flew around the Naval Observatory in Washington, D.C., that people began to accept heavier than air flight, like 2 or 3 years after Kitty Hawk. So I think that there's a problem we have in the United States, in particular in the energy area, and I'll point the finger directly at the Department of Energy, but also, in scientific research in the United States and throughout the world, in the way that we do science and the way that we do not allow room for new entrants, and the penalty that scientists pay for trying to get into, introduce a new area. And by the way, the area I'm most interested in is cold fusion.
So if I may just briefly comment on that. Well, no, let's have more questions, and I'll come back to that. Yes, go ahead.
So you've been talking about energy innovation, the need for it, primarily in low carbon approaches. How do you think it's going to handle the kind of the inertia, the industry that already exists with high carbon technology? And it's still innovating, I would think. Fracking is an innovation that's increasing the use of fossil fuels. I guess how is this going to be able to compete with an industry that's already innovating?
I mean, that's of course, in a sense, the central problem. We've got highly optimized, highly efficient, and becoming progressively more efficient incumbent fossil-based systems that constitute the competition. And it's a very, very tough task. And, are we going to succeed? I don't know. But what I do feel confident about is that if the strategy is purely one of trying to raise the price of the high carbon incumbents, it's not going to work politically and for economic reasons also. So it seems to me that our strategy should focus on trying to bring the costs of the high carbon options down. It's going to be very, very hard to do. In some cases, I think we're getting much closer. But I'm agreeing with you. This is an extremely tough challenge. These are systems that have been honed by highly capitalized, very influential politically, large incumbent organizations. That's the competition. And that's why this is a much tougher innovation task than, for example, innovating in information technology or telecommunications, where it's really been historically about creating entirely new markets, new products, new services. Here, this is grinded out, cost reducing. It's the toughest kind of innovation where the competition is extremely capable and extremely influential politically.
So what do you think the primary driver is going to be for this innovation? It's not going to be government subsidies or, as this gentleman said, scientists. Where do you think the drive for this sort of innovating that you're talking about is going to come from?
So I think we have to create a system that looks different from the one that we have been relying on until now. If I may, I do want to come back to the point that you made, because, and then I'll come back to this. On this issue of new entrants, I don't want to disagree with you on the question of how science is done. I mean, I think it's an interesting debate to have, but the point that I would make in this regard is that, and this may sound strange coming from someone whose background is in science and engineering, but we are not going to be bailed out by discoveries that have yet to be made, or even by discoveries that are currently sitting on people's lab bench. Because the time frame to move such discoveries to the point of commercialization and then to achieve significant penetration in the marketplace is measured in decades. And we don't have that much time. So what this means is that we're going to be relying, for the most part, during the first half of this century, on technologies that we already know about. They may not be commercial, they may not already be in the marketplace, but we know about them, we can point to them, we can talk about their economic characteristics and engineering characteristics. And when I talk about the need for new entrants, I'm actually talking about the need for new entrants into the marketplace rather than into the sort of field of science. I think it's an important debate to have about how science is done, but if we're looking at what has to be done over the next few decades, what we see is what we're going to have to work with, and we're going to have to improve somehow the cost characteristics of these things that we already know about.
History has shown, however, that truly revolutionary discoveries will quickly be deployed on a much faster scale. For example, the automobile displacement of a horse, or we built the entire aerospace industry in something like 20 years in the United States. So the truly revolutionary innovations, I think, have a potential for much more rapid deployment.
If you look at the history, I mean, let's take solar. I'm a big solar enthusiast. But we know, most of us know, that solar is now contributing, 0.2% of our electricity. The fundamental invention 60 years ago, 70 years ago, it takes that long. Let's take nuclear. Nuclear, people have forgotten this because it's a long time ago, but actually, if you look at the post-war period, the fastest market penetration of energy, of any new energy technology, was what happened with nuclear from roughly 1970 to about 1990. And during that period, nuclear started out at 0%, and it ended up at about 20% of the US electric power system in 2 decades, 20 years. That's the fastest that we've ever done anything in the last several decades. And I don't think it's realistic to expect much more than that. And so what we're talking about here is these are huge systems that will take a long time to transform. And I hope that we will have these breakthroughs, but I see them as contributing primarily in the second half of the century. Let me just take, I know people have got to leave, but let me just take 2 minutes to sketch out what I think may be an alternative approach. Can I just take? So, and I don't want to claim that this is the only such approach. Certainly I don't want to claim that it's the best one. But I want to use it as an example to illustrate some of these design principles that we should have in mind when we think about what the U.S. energy innovation system could become. And it starts with, I'm going to call them regional investment banks. I'll call them RIBs, that would focus on these 2 intermediate stages of the innovation system, demonstration and early adoption of, in particular, low-carbon energy supply technologies, both centralized and decentralized. That's the second wave of innovation that I talked about earlier. These entities would be investing in innovations that at present are expensive relative to the incumbents, maybe inefficient, but have the potential to descend the learning curve, as we think and hope might be the case with solar photovoltaics and other technologies. The projects that would be proposed to these RIBs, Regional Innovation Investment Banks, would be proposed by many different kinds of teams, individual firms, groups of firms, partnerships that might include established firms, entrepreneurial suppliers, power producers, labs, even universities. And these would in a sense, in effect, bid into these regional innovation investment banks. And one of the principles here that you see is that the system would be opened up to new players and new combinations of players. The teams that were proposing projects would seek funding from these regional entities not as the sole source of finance, but rather to augment their own investments and reduce their risks. Think of it as a risk-reducing thing. And the RIBs would use a range of options, loans, loan guarantees, interest buy-downs, equity infusions, and the investments by these RIBs would leverage larger amounts of private sector funding. And here's another principle, design principle: try to fill this financing gap in the intermediate stages of demonstration and early adoption. Like venture capitalists, these RIBs would choose among competing proposals based on, the strength of the team, the quality of the management, the attractiveness of the technology, the extent of self-funding, and so on. There would be several of these banks around the country to allow for differences of opinion about what's most promising, regional variations in what's most useful and acceptable. And indeed, over time, one might expect these regional banks to specialize in areas of particular interest in their region. So, for example, offshore wind in the northeast, nuclear perhaps in the southeast, carbon capture in the Midwest, and so on. But an important principle here is one of pluralism. Project developers would have the option of approaching more than one of these banks, maybe all of them, and not having to deal solely with the federal government, which is, in a sense, the way things work now. There would be a check on the process to make sure that it doesn't become too inbred. There would be, not shown on this diagram, a federal gatekeeper that would certify that an innovation has the potential to lead to significant reductions in carbon emissions at a declining unit cost over time. And the role of the gatekeeper wouldn't be to determine whether a specific project should receive funding, but rather it would be responsible for certifying, for saying, yes, this is a project that can legitimately present itself for funding from these regional banks. And if a project, if a technology was not making progress, the role of the gatekeeper would be to decertify the project, trying to avoid the worst pathologies that we've had in the past of zombie projects that won't die. The last two pieces of this scheme have to do with the funding. Where would the funding come from? Well, here the proposal is to have a dedicated funding scheme based on a surcharge on electricity use. If you do the arithmetic, you would discover that a 0.2 cent, 2 mil per kilowatt hour surcharge would generate roughly $8 billion a year, leveraging perhaps 2 to 3 times that much in private funds, $20 to $30 billion a year. That's roughly the scale that we need for this problem. It is an order of magnitude more than we're ever going to get over the next 10, 20 years from the federal government. The cupboard is bare, and it's just not plausible for the federal government to be making those kinds of investments. So again, the principle is the scale of the system, the scale of the effort must be commensurate with the scale of the problem. By the way, a surcharge of 0.2 cents per kilowatt hour would add roughly $1.80 per month to the average household residential bill. these banks, these regional banks, wouldn't have an entitlement to the surcharge in the scheme. They wouldn't be guaranteed to receive the funds. In fact, what would happen is that a trustee organization at the state level would disperse the funds collected from ratepayers based on their assessment of which portfolio of projects, which regional bank's portfolio of projects most closely corresponded to the needs of that particular state trustee. So what would happen in this scheme is that the boards would compete for these funds. So you've got competition occurring at two stages: the projects competing for funds from the banks competing for funds from the state trustees. So, you know, the basic principles here are: it's a bigger system that than we have today. It's more comprehensive across the innovation life cycle because it addresses these two intermediate stages. It's more pluralistic. It's more open to, or would be more open to, new entrants. It relies more on competition than the current scheme. And crucially, it's more accommodating of regional variation. We know that different regions of the country have different resource endowments, have different capabilities, have different public attitudes towards different technologies. And one of the problems, one of the roadblocks in the system that we have today has been not partisan politics, but actually regional differences preventing Congress from moving. This is a scheme that would, to some degree, provide more authority to the regions vis-a-vis the federal government. So I could talk a lot more about this, but I don't mean to suggest that this is the only alternative to the current system. In fact, I would encourage everyone here to be thinking about other alternatives that may be better than this. But the bottom line, what I'd like to leave with you is the thought that I almost started out with, which is that I think we have to be as creative about the design of the system within which new energy technologies develop as we are, and we must be, about the design of the energy systems themselves. So this is a class which I think probably thinks about these things, and I would encourage you to think about alternatives because we need them. We can't, and we won't have an opportunity, we won't have a chance of achieving this enormous transition unless we can accelerate the pace of innovation, and we need new institutions to make that happen. So let me finish there. I apologize for going on too long, but thank you for being so patient.